Good morning, good afternoon, good evening, or wherever you are right now. So my name is Eric Boisvert. I work for the Geological Survey of Canada in Quebec City. I'm now the program manager for the Groundwater Geoscience program, but previously I was more involved into data standards, and I've been actively contributing to GeoSciML. So I'm using the NRCan template right now because I could not decide between an OGC, IUGS, or Montreal hockey teams just to annoy Boyan, but I might actually revert to an OGC background after for the official version of that presentation. So GeoSciML, that actually stands for Geoscience Markup Language. It's a GML application. It's a standard really for transfer of geoscientific information that we commonly found on geological maps. What you'll find in the specification is both a UML model and an XML encoding of that UML. So it's hard actually to present everything about GeoSciML in really 20 minutes. So there's a lot of documentation on the web, and there are far better presentation. Actually, if you really want to have a deep description, a deeper description, I actually suggest that you look at the presentation from Ollie Raymond in 2015 that make a more complete description. So I will probably just fly over a lot of information, and you can find a lot of material on the web. So really the goal of GeoSciML is to make possible the integration of data from multiple sources using a standardized machine readable form. And I insist on machine readable form because now we're getting more and more into the age of machine learning and big data. It's already being used quite extensively by a lot of initiative and information systems such as One Geology, Inspire, USGen, OSGen, that also includes the RML extension that Michael will talk a bit later. We have a groundwater information network that actually use a groundwater extension of GeoSciML. There's EPOS, GeoEra, and you can also find the QGIS plugins that can read GeoSciML right now. There's one from Icelandia that can read the borehole, and also BRGM has been working on a complex feature plugin. So, but why? Initially, the idea was to gather the information for geological surveys into a single unified system. So you can just read the information and from a database as they are structured. So the idea would be that each of those data provider would just keep their data model as they are and just do the mapping and just push this data up to the web using the OGC specification at that time. That was WFS. Now they are transitioning to OGC API. So the system would have a seamless access to multiple data sources. The idea is that client application could just read from wherever sources without knowing exactly from what the data source is, and just simply use a single standard format in the old rule of the one ring to rule them all. So that was the initial goal of the initiative. But there are many things that you can do with the GeoSciML just as a repository for a representation of a whole map, more than just a system. So you can archive data in GeoSciML as well. So the work itself is an international effort that started in 2003 in Edinburgh. It involved geological surveys from many countries and also a lot about server. And the development has been under the auspices of IUGS, a special group called CGI, that you're actually organized this workshop. And eventually, around 2013, we actually had a memorandum of understanding with OGC to have this specification published as an international official standard. So OGC is an international body for standards. So right now we are at the fourth major version, but we had about 15 releases. It's built on previous effort from such as the XML from Australia, from the North American data model, which is a joint collaboration from Canada and US, JXML from Japan, and also we imported other work from OGC, so observation and measurement, metadata, sensor web enablement, which provide us the way to how to structure numerical data types. So the first version was a one big monolithic model of into a single schema. In version 2 in 2009, we actually regrouped the properties, but it's still monolithic, and we had boreholes and fossils. Version 3, we packaged everything into 13 different schema just to keep it manageable. We had the geomorphology. We actually externalized the vocabularies, so now it's its own piece of information. And we also made all the property mandatories. But at some point, somebody said that this is way too complicated. So we reverted back instead of having 13 schema based on themes, we reverted back to a basic and extended. So a simple model and a more extended. So when people need very specialized representation. At this point, it has been published on the OGC standard in 2017. And also we pushed the idea of a profiling, so people can use schematron just to create their own profile of GeoSciML and just decide which properties should be mandatory and which should be optional. And also we included into the stack what we call the light model. It was called portrayal before, but portrayal actually means something different, so we have to change it. So what's the scope of GeoSciML? It actually covers geology. So earth material, geological units, stratigraphy, geomorphology, pretty much the stuff that you find on geological map, but also has the sampling features, which is the human things that we actually use to observe the earth. So borehole and specimen. It also has that GeoSciML, the portrayal, which is the simpler version. And it does not address the more specialized science domain, such as hydrogeology, but now we have a specification called GeoSciML, groundwater ML. There's seismology is not covered, geophysics is not covered. Economic geology is covered by another specification that Michael will talk about, the GeoSciML. And also it's important, it does not cover symbology. So GeoSciML won't tell you this unit should be green or yellow, and doesn't tell you which symbol you should use for a structural or for a fault. So in a nutshell, I won't cover all GeoSciML because it's pretty much like an hour presentation. So what you get in there is pretty much the core of the model. So you have a map feature, which is the stuff that you find on a map on the real world of the geometry. And then you have the, I think I can use this, where is it? Oh, there you go. There you go. Okay. So map feature is basically what you find on a map, and the geologic feature are the geological things that you can map, and those geological things are subdivided into different kind of things. So structure, units, geomorphologic feature, and events. And events are basically what has an age. And these things have history, and geological feature are related to other geological feature, and that's pretty much it. So these things are further subtyped, but it's pretty much the core of the model if you exclude borehole and geological age, which are basically their own things. So if I just note here because I don't want to flash too many XML in your face, so it's usually pretty ugly. So map feature and geological history and geological unit and geological event, you'll find into, just keep an eye on them. So this is an example of another way to put it. You have a description of what typically you find on a map. So this is a piece of in Arizona that we also use in the specification. So map is one way to represent it, but cross-section is other way to represent it. So it's agnostic of the way you represent the information. So the ugly XML looks like that. So you can find my geological unit is here, map feature is here, the geological history, geological event, and you have that bunch of information, which is just structure, all the information you can find on a map. And this makes it machine readable. So the machine can actually extract this information and do something with it. So this is the whole point of the exercise. So it was also a bit too complex. So we have a light version. So a light version is simplified data standard, which looks like a shapefile. So a shapefile is basically one row of data by geometry. And it's also compatible with existing software, which is use very simple representation. It has a limited expressiveness, so you have to compact everything into into a single line, but you have a lot of a simple application that you can create with that. So as an example, you see the XML is already simple because everything has been flattened as a single row of text. So this is what we call GeoSciML Lite. We have a couple of entities that we create as Lite. So you have borehole, geological units, structures, samples, and you can expose these things using a much simpler technology. And this underpins a lot of the existing portal right now. USGen, OSGen use this. To One Geology portal also uses the portrayal or the light version. So there are extension of GeoSciML, and this is so it's being reused, and also the concept expressed in GeoSciML are being reused in other specification. So we have one for groundwater ML that just reused GeoSciML and extended to just include the hydrogeology topics. We have Earth Resource ML that Michael will talk about later that concerns mineral and mining activities. We used to have Soil ML. I don't know if they're very active, but back then, I think it was an initiative from Australia and New Zealand that want to include soil geology also as an extension of GeoSciML. And now we have Geotechnic, and I think this has been spearheaded by BRGM right now. And a lot of initiatives actually leverage the vocabulary. I think if something has been picked up most is the vocabularies, and a lot of work is being done just to create ontologies, and Boyan and Steve will talk about that a bit later. So a lot of activities about vocabularies seems to pick up, and that might actually be the next cycle of innovation on GeoSciML, just to create a formalism on vocabularies for machine learning. So what's next? Right now, what we're working on, OGC is transitioning from XML to a more JSON-based API, although it's not mandatory, but it's an expectation that JSON is going to be the new format. So we're right now working on JSONify the encoding that we have right now. So we're calling for contribution. So we're looking for help. We started work on the GitHub account for GeoSciML. We started looking a bit of the existing JSON encoding and what would be required to make a compliant GeoJSON representation. And also, since GML has a lot of potential to be used for knowledge encoding, knowledge representation, we're also looking into RDF encodings. And one kind of RDF encoding, which is a layer above, is called HOW for representation, and Broderick and Richard presentation will tackle that. So in conclusion, GeoSciML is right now an XML-based format to exchange geoscience information. Despite numerous versions, all the versions that we have, they are quite robust. So a lot of the change that we had from one model to the other model was really looking at formalism and technology. But if you look version 1 to version 4, you can pretty much recognize the same model. So I think we nailed it pretty much in 2003 or 2005. And we just keep fiddling just to adapt to different technologies. And this is what basically we're doing right now. We're slowly moving to adapt to new technologies. So a lot of internet resources. So you'll find that into the presentation. And thank you. And this is just to annoy Boyan because probably the Habs are going to the final of the Stanley Cup. So, here we go. Thank you.
Thank you, Eric, for that very helpful overview and sports-related provocation. That is good. So who has discussion for Eric?
There's a lot of stuff in the chat box. I don't know if there are questions in there.
Indeed. Yeah. Simon Cox mentions that Soil ML is, he doesn't think it's used or maintained anymore. And there's also been discussion following on Mikhail's opening talk. And so who has a question or a comment related to the presentation of Eric Boisvert? Please type in the chat or unmute and go ahead and speak.
There are mostly comments in the chat.
Okay, so Eric, would you like to follow up on anything in the chat or shall we proceed?
No, thanks to Simon. I wasn't sure about soil ML, but I Googled around and it's been quite dormant for many years. So I think it's been abandoned.
Very good. Okay, thanks again,
Oh,
Eric.
oh, oh,
Okay, all right,
there's a
Gabrielle.
question from Gabriel.
Yeah, why is deciding to have JSON versions of OGC standards, Eric?
Oh, well, to be blunt, web designers, web developer actually use JSON as a way to transfer data from server to the browser, because JSON is basically a JavaScript object, so they don't have to do any parsing. So it's the new kid on the block thing. A lot of people knows my opinion about JSON. I think it's not as good format as we can actually use. XML and RDF are much better, but this is the format of the web. So people actually use JSON and expect JSON to create application. It's lightweight, it's easy, and your browser actually understands it without doing anything special. It just consumes it. So that's why, pretty much. Don't cite me on that, but that's pretty much the reason.
And Miguel adds, GeoJSON is quite special. First, GeoJSON is not an OGC standard. The new OGC API features propose to have it as a possible output, but as far as he knows, there is still this issue with addressing CRS different from WGS 84.
Yep, but GeoJSON is popular. So.
Okay, further discussion. And we have chat contributions. UNESCO Center Integrated Survey. All right. Okay, final chance for discussion on Eric's talk. Thank you, everyone. So Michael Sexton, please go ahead.